Now we are going to get into how the different components contribute to the static longitudinal stability. So we seen that these two variables, the y-intercept and slope, is the one which decide whether we are going to have the longitudinal stability or not. So we will first look into what is the contribution of wing to the longitudinal stability. And when I say contribution, basically we are going to look into how this wing is contributing to this y-intercept, which is over here, this particular variable, how it is going to contribute, and how the wing is going to contribute to the slope. So we have, before getting into the mathematical details, first we look into this figure over here to understand some of the variables, so that it will be easier for us to look into the maths which is further down. So we have here center of gravity, which is CG. We have the lift and drag acting at the wing. These two are the forces. Then we have the moment about aerodynamic center of the wing, and then we have angle of attack for the wing measured between the chord line and the relative wind. We have wing incidence angle measured between the chord line and the nose of the airplane. And then we have this x distance is distance between the leading edge and aerodynamic center, and xcg is the distance between the leading edge and center of gravity, while z distance is a vertical distance between the relative wind and the center of gravity. We should always remember that lift always act perpendicular to the relative wind direction, while the drag act always in the direction opposite, in the parallel to the wind direction. So now we understood that figure. Now what I am doing here is just I am translating this forces over here to understand it better. So because of this angle of attack and wing incidence angle, we can see that the lift and drag acting on the wing is rotated by this particular angle, which is alpha w and iw. So we have these two forces acting on the wing, and we will resolve these forces in vertical and horizontal component. So lift will have the contribution over here, and lift will have contribution, horizontal component is over here, and then drag will have contribution in the vertical direction, and drag will have another contribution in horizontal direction. So when we will take the moment of all these forces about the center of gravity, we can write in this form, where MAC is the moment about the aerodynamic center, and these are the lift contribution, and these are the drag contribution. We also know that we can express the moment and lift in terms of coefficients. So we can write the moment and lift in terms of coefficients like that, and when we will substitute this expression in this main equation over here, we can reduce that in coefficients, and this will have give our moment coefficients about center of gravity from the wing, where you are seeing the terms which is a star, denoted a star here for the simplicity, and that star is just the alpha w minus iw. We have some assumption involved here. We are considering that our lift is much more bigger than the drag, and the vertical distance which we seen over here is, we are saying that it is very small than the horizontal distance measured with respect to center of gravity. So when we will substitute these assumptions in this particular equation, we can reduce this big equation in this simple form over here. Now in this equation we can see that we have a lift coefficient over here, and we know that we can express the lift coefficient in a straight line equation, like when we draw the lift coefficient curve between the angle of attack and lift coefficient, we get the y-intercept and the lift slope. So when we will substitute this particular expression in this, replace this lift coefficient with that, then we can reduce that to our moment about center of gravity in this form. Now this is our equation 1, and we've seen that from the straight line equation we can also express the moment about center of gravity in this form, where this is our y-intercept and this is our slope. So when we will compare this equation 1 and equation 2, we can see that this is going to be the contribution from the wing to the moment at zero angle of attack, and this is going to be contribution from the wing to the moment slope, right? So this is what we was initially when we started on the top. You can see that we wanted to know that in this particular variable how much the wing is going to contribute, and in this variable how much the wing is going to contribute, and that is what we have here. If we go down, that is what we have here. So this is contribution from the wing to the moment at zero angle of attack, and this is contribution from the wing to the moment slope. Now we discussed the criteria for having the longitudinal stability is that the moment slope must be negative. But to have the slope to be negative, the center of gravity must be ahead of the aerodynamic center. Then only this moment slope is going to be negative, but that is not in the practical case. Generally we observe for the airplane to have the center of gravity behind the aerodynamic center, and in that situation this moment slope is going to be positive, and that is what we don't want. We want the longitudinal stability, and we want the moment slope to be negative. So this gives a sense that the wing contribution to the slope is going to be destabilizing because it will have the positive moment slope. Now looking at the moment at zero angle of attack, if we consider at zero lift, so at zero lift, this term will go to zero because we don't have the lift at zero angle of attack, and in that scenario our moment at zero angle of attack is going to be moment equal to moment about aerodynamic center. And generally in the wing we use either positive camber airfoil or zero camber airfoil. In that scenario, when we have the positive camber, the moment about aerodynamic center is negative, and if we have the zero camber airfoil, the moment is about aerodynamic center is zero. So in either of these two scenarios, the moment is going to be either negative, moment at zero angle of attack is going to be negative, or zero itself. And that is what we don't want. When we was discussing the criteria, we said that the moment at zero angle of attack must be positive and slope must be negative, but we are seeing that for the contribution that is coming from the wing is different. So this leads to our general understanding that the contribution of wing alone to the longitudinal stability is in general is destabilizing. So this is what we had for a straight line for the moment line. This is y-intercept and this is slope. So for the moment coefficient we need the moment at zero angle of attack and moment slope multiplied with the angle of attack. So this is what we've seen, the moment contribution of wing to the moment at zero angle of attack, that is over here, and this is we seen the moment contribution of wing to the moment slope, that is coming from here. So we observe that the wing contribution to the static longitudinal stability is mostly destabilizing.